Fourie. I want to be talking about service chaining for OVN. It's interesting that I believe there was a talk about a year ago, a quick talk on service chaining for OVN. So we've moved forward a little bit since then. And what I want to do is essentially with John McDowall, Farhad, Sunavala, and Flavio Fernandes talk a bit more about what we've done and how we intend to, or propose how to do service chaining within OVN. Okay, so this essentially started with work that was done within OpenStack to add service chaining into OpenStack. And this was done about a year ago. We added it into the Mitaka release. And what we've done is essentially add some additional attributes for Neutron that will allow us to express service chains in terms of a sort of essentially a unidirectional port chain. And that would comprise of a number of port pair groups. So each port pair or each service function is represented by a port pair. So that would be the ingress and egress ports of a service function. And what we can do is combine them together into a port pair group that would allow us to do load balancing over the number of similar service functions. And then those port pair groups are chained together to form the chain. In addition to that, we have a chain classifier, which comprises essentially the source and destination in tuples, and these control the traffic that actually goes into the port chain. So shown at the bottom essentially is a number of service functions, and there are different instances for each one of them, and the structure that we have allows an application to make requests to create and delete these resources to actually create the port chains. We have the flexibility to do updates on the port pair groups to add and remove individual port pairs. So I should actually clarify that each port pair is based on Neutron ports. So you have an ingress Neutron port and an egress Neutron port. So what you see there is essentially a number of different port pairs grouped together in port pair groups. Okay, so what we were thinking is how we would take what we'd done within OpenStack and map this into OVN. And essentially what we did was take those resources that we had within OpenStack and map them onto tables that we would add into OVN. So these tables would be added into the OVN northbound database. And what you see there is, you've seen probably a similar diagram with the existing logical switches, logical routers, and logical switch ports. What we're doing is intending to do is to add an ACL extension to the ACL. So we'll add an ACL action with a SFC action, and that would then direct the traffic that matches the ACL into the port chain. So we then have the port chain. We have another table called the port pair group table. The port pair tables and those would reference the individual logical switch ports. Looking at in terms of the architecture, so this kind of replicates what exists today in terms of the Neutron API. So we have sitting underneath the ML2 mechanism driver for OVN, and that's then integrated or interfaces with the OVN northbound database, inserts, creates various logical switches based on networks being created within the Neutron structure or networks. And then what we've done is extend that so that we can then use our networking-sfc Neutron extensions to then map to extensions to the northbound database. And then those would then be mapped onto flows that would allow us to actually create the port chains. So to dive into a bit more detail, this is the actual schema that we've extended. So we've added, based on what I've shown in the previous diagram, is the logical port chains, the logical port pair groups, and the logical port pairs. And you can see, for example, for the logical port pairs, we have an ingress or an in-port and an out-port, which references a logical switch port. And then we have the others that reference the port pairs. In terms of extensions for the ACLs, what we've done is added an additional action that would be an SFC action. And then in addition to that, we would have an option that would allow us to actually reference the port chain that the traffic would then be driven into. So those are the only extensions that we added to the northbound database. In addition to that, we've obviously had to extend the northbound commands, the CLI commands, and you can see there really those are the set of commands that we would add, and also the extensions to the ACL add command. Okay, looking at the kind of rules. So this represents a logical switch, and we see the service functions attached through ports. At the top there, we have a set of 3 service functions. We have source and destination traffic for the traffic, and then what is shown in yellow are all the rules, the logical switch rules that are used to actually steer the traffic. So, for example, we have 2 chains there, chain A and chain B. The one chain passes through service functions 1 and 2. The other one goes through 1 and 3. And essentially what we do is we create, based on the definition of the northbound resources and the tables that have been added, we map that into flows that are installed in the ingress pipeline in the southbound database. So what you see there is a number of flow rules, simply indicated as the R0A means that a rule on port A is going to do the matching for chain A, R0B is on port 0 is matching for chain B, and so on through the network. And to date, we've actually got this implemented, and what I'd like to do now is hand it off to Flavio, who'd kind of work through a demo that we have.
Yep, sounds good. So I did my share of sacrificing, so I feel actually pretty good about the God demos, but we're going to do a recorded version to interest of time. I have this posted online, so you guys can all follow along with that link over there. You see where it is? Yeah. Cool. I'm going to make it screen. Yeah. Right. So yeah, what we have here is that just a couple of VMs, and then inside of them we have some instances, and normally what you'd have would be the instances, and for in case of port chain, you have the VNFs. So in this example, I'm putting out the VNFs on a specific compute node, so I can actually look at the logs for how the traffic flows. So in this example, I have a bunch of chains, actually 5 chains, but in this case, we just focus for this demo on this one, where I'm taking the traffic from instance 1 to instance 2 and forcing it to flow through 2 VNFs. And I think I'll show you the other chains here, just to show you the spaghetti you can actually come up with. But basically, all of these would represent different chains that you can program OVN with, and with the logical flow rules, you can actually make it take those paths, even know what they are, what they're logical for. If there's any questions, just interrupt me anytime, guys. So yeah, so here I'm just showing this little Golang program that I had that we actually run inside the VNFs to pretty much take a packet in, and this is a bump on a wire implementation where we're really not changing the state of the packet as it flows from one VNF to the other. So we're just taking a packet and sending it in and out. And here are just pretty much the configurations. I'm not sure if you guys can read this, but basically it's just an example of what Louis was showing before of the commands for creating the chains, the port groups and the port pairs. And you basically associate port pairs to port groups to dictate how the chain wants to flow the packets as they go around. So yeah, so here I'm creating the port pairs, the chains below, the the port groups. So in this case, and if you remember on the first example, the chain 1, 2 had 2 VNFs. So here, if you see, there's a port group hop 1 and hop 2. That's why they have 2 instances for the port group add commands. Yep, they're below there. Yep. So yeah, those 2 port groups. And then you associate the port groups to the port pair. So think of port pairs as something that you would load balance in, and think of port groups as the list of groups of ports that you want the chain to visit from beginning to end. And then at last we have the classifiers, like Lou was talking about. We had the SFC action, and then we expanded to take the options as a way to populate it. So here we're pretty much just starting the OVN cluster and running the script that pretty much configures all the chains. I'm doing some show commands here to show you pretty much the northbound, what it looks like in this example, followed by the southbound, so you can actually see the ports of the VNFs bound to compute 3, and then compute 2 having 2 instances, and compute 1 having 1. And here I'm pretty much showing the output of the chain command, basically showing the chain 1, 2, where you have 2 port groups, and inside of them the port pairs that go with them. Here I'm showing you the actual logical flows and how they get programmed by the North D. So these are, when you configure the chain, we have the classifier rules, and then you have the chain rules to pretty much dictate how the packets would flow from beginning to end, given the classifiers insert them into the chain. And here I'm actually using bends to the OVN trace tool, where it's a really nice way of actually showing how the packets flow into the chain without actually even having the port bind, in this case. So you pretty much tell, I want a packet that looks like this, and given this input port, what's the output port? And it's actually nice that you can change the input port as you modify the chain, and you can see it hopping from one to the other until you get to the very end where it's supposed to go. So here I'm pretty much just starting the app. Like I said, I was starting it on compute 3, so I have logs of when the packet hits the VNF that we can see it happening. So here I'm just pretty much sending a ping from instance 1 to instance 2, and then going to compute 3 and showing the output of the packets as they hit the VNFs. So I can pretty much see that VNF A got hit and VNF B, and then the answer came from VNF C, like it's showing here on this graph. And I think, it's one more, is here I'm doing the same thing for 3, and in this case, VNF C is the one that gets hit. That's what the last 2 log lines enter there are showing. And I think that's it.
Great, thanks, Flavio. So that's sort of what we've done today, is we've been able to actually demonstrate that we can go through the create a port chain as we've shown here. So what we would also like to look at now is how to handle the load balancing. So what we show here is having some form of load balancing operation where traffic would be sent to a port chain, or rather a port pair group that consists of more than one service function. So what we see there is port pair group X, which contains 2 service functions, and the load balancer rule X essentially is the thing that drives the traffic and load balances the traffic across those 2 instances. And what we would see, potentially what we could do here is to actually extend the load balance operations that have been added to OVN to be able to do this. So we could then load balance to a set of input ports for a number of different service functions. And essentially what we show here is the two different chains. Each one of them would allow the load balancing operations to occur across those two service functions. So in terms of what we do in the ingress pipeline, how we would actually implement this, and what we've done to date is that we've actually added additional tables in the ingress pipeline. There's a service chain pipeline, or a service chain table rather, which actually does the has all the rules that do the steering that we've shown already. And in addition to that, what we're thinking, we would also have some form of extension to the load balancing table that would have operations to actually do the load balancing to a set of ports within a port pair group. So to actually look at the changes that we would need to add to the ingress pipelines, so we would first of all need to change the L2 security table, because for any given service function, we could have traffic passing from many different sources and destinations with different MAC addresses. So we'd need to make changes for that. We'd also add a chain table. This, as I mentioned before, would have rules that would actually be able to steer the traffic. And the idea would be to have some mechanism where you'd actually do the matching. This would include classification on the initial ingress from the source VMs or the source logical ports through to reclassification from the out ports from each one of the service functions. That would be handled by this chain table. Then in addition, we would probably add some form of port load balancing table, and that would have the operations that would actually allow us to do the port balancing. Shown at the bottom essentially is a rough idea of what we would have there. So we would have some sort of match. So this match on some form of metadata register, that would be actually set by the chain table on a match on a particular chain. It would then be driven, or a number of chains would be driven to a specific, have a specific metadata value that would drive to a specific port pair group. And that port pair group would actually have the action to drive or load balance the traffic to a number of different port pairs. Okay, so what we've described so far is really service chaining on a single logical switch. What we'd probably like to do is to be able to have service chains that actually span multiple logical switches. And what we show here is, in fact, 3 logical switches, and they would be connected via a number of logical routers. And what we would have to do is, on the logical routers, to have some sort of source routing where we'd have rules installed on those logical routers to actually steer the traffic that comes in on a particular patch port to a specific outgoing patch port to a logical switch that would have the next hop service function on them. This is work we haven't done yet, but we're working on it. Anyway, I think I must end here. I think this is just some information in terms of where the source code repositories are and some additional work that we want to probably discuss with the OVN group. And we're open to take questions. Maybe one question?
Hello. Thank you for this talk. I have one question. I was not quite clear. The classification, is that only done once, and then you have basically hardcode to change to a set of dedicated port pairs, or is the classic packet reclassified every time it comes back from the service function? You apply the same classification over and over again?
That is correct. We would do service classification again and again at each port. Now, that presupposes that the service functions are unaware of some form of service chaining header that might be attached to packets. If that's done, then You would then match on maybe some form of network service header, the identifier, and then steer based on that.
So yeah, just to complement your answer, your question on classification that we use for the ACLs, we actually explicitly give the import. So that's one way you can skip the ACL as you enter the chain, as you continue through the chain, because it really is a full-fledged match syntax that you have available to you at that point.
Okay, stupid question here. So is this, I see you talking about NSH here, so what you have so far is a pure control plane solution, that there is actually no carrying through encapsulation of NSH header?
Yeah, we did it that way to make it, to get started, because if we rely on NSH, it would take us several years to get stuff done. So the goal here is to get something that works, and we can add to it.
Well, that's impressive.
So one question I have is there was at least one service function chaining proposal described a couple of weeks ago in Barcelona. Is this the same one? Is this related?
Same one.
Okay. I guess I understood it differently, so I appreciate this this presentation. It was clearer to me.
So, which one in Barcelona? Because there was 2 or 3 in Barcelona.
There was one in Barcelona where the way I understood it, the packet left OVN to go to a service chain, and then there was not much of a. It didn't seem like there was much of a description of how it came back into OVN. And to me, this one, I think this is a different one because it seems to stay in OVN the whole time.
Yeah, it stays in OVN.
Okay. So have you talked to other groups who are working on SFC and OVN?
I believe we're the only group working on it right now. I mean, John's presentation in Barcelona was essentially what we were talking about here.
Okay, then perhaps I just misunderstood it.
Well, was that Intel presentation, or was it?
I thought it was a discussion in one of the networking Neutron work sessions, maybe.
That was us.
That was you.
Yeah.
Okay. Well, then I misunderstood the Barcelona presentation.
Okay, sorry. That was my fault.
Well, now I understand it better, so it's good. Go ahead.
Thanks for the talk. In all the diagrams, I saw that the chain was defined in a single direction. So I just want to know what is the rationale for not defining or not automatically defining the chain in the other directions. In my past experience, I've seen like things like L7 straight to firewall, service directed traffic to go through the firewall. So I just want to know what was the rationale for not automatically defining in the other direction.
Bidirectional chains can easily be built up, with two unidirectional chains. So this gives you the fundamental building blocks for that.
So the actual code today is bidirectional. But I agree with Louis that we should build it as 2 separate chains, because you can use it as building blocks then. Because if you have if the default is bidirectional, then you can't do single directional.
A Neutron API does have a symmetric option. So if you put the symmetric option, you can build up bidirectional.
All right, let's thank all our speakers one more time.